And welcome back there, folks, for part two of the lesson 1.3. You've done your in-class fun and learning, and you're ready to make sure that you got out of it what you were supposed to get out of. This is this video. Zeros and factored form conclusions. The expectations are to make connections between a polynomial function in factored form and x-intercepts of its graph. Well, I just want to point out, before we get into what we did today, in the 3-minute review, this was a parabola in factored form, and then we saw what the roots did. This is a parabola in vertex form, but we could also see what the zeros of this function, where it was this purple function was right there, and similarly this green one was at -2, and in fact this is what you were supposed to find today in the activity. So let's get into it. So in factored form, we have a polynomial where it's x minus, and this is a number. Don't get too caught up in the notation here. The x1 and x2 and x3, these are all numbers like 1 and 7 and -3 and that sort of thing. So first of all, it has zeros at x equals x1, x equals x2. So these are all zeros, spots that we can put dots on the x-axis. So for instance, we know that it has a 0 at x1, so we'd put a dot there. There's x1. And even more than that, you're supposed to sort of get this idea of the shape of the graph for each of the exponents on the bracket. So slashes for linear factors like this. So for instance, we know that if there was only an exponent 1, implied 1 there, that near x equals 1, the polynomial function behaved like a line, a linear factor. We don't know that it necessarily went this way. It could go this way, but it sort of slashes right through, and that's a Restall description there. You could think of it however you like. I think of that as a slash. There's only one bracket there, and so it slashes through. But if I had a squared factor, like this middle one, the squared factor, then at x equals x2, then it bounces. Right? It bounces like a parabola, right? It behaves like a parabola. So we knew that was a 0, but near there, the function behaved like it looked like a parabola. And notice that's what we saw in the 3-minute review, right? Near x equals 3, it behaved like a parabola. Then similarly, and I called that a bounce. Then what happens if it's a triple root, a cubic root? Well, cubic factor. And notice, by the way, the bounce, we don't know whether it happened down, like up, like, because it could bounce this way. And we saw that it could have bounced this way. We don't know. We have to think about it more to decide whether it goes like this or like this. But at a cubic root like this, then it behaves like a cubic factor, like a snake shape, or what I called a slide. It looks like it's going to bounce. It comes up, slows down, looks like it's going to bounce, and then slides through. There it slides through like a snake. And so near x equals x3, it behaves like a cubic graph. It behaves like this graph, and we saw that here. It looked like it was going to bounce, but then it slid through at x equals -2 in the 3-minute review. Dandy. And that's what you were supposed to come up with. Now notice again that it could slide this way, or it could have slid this way, right? And we don't know, right? We know that it behaves in this snake pattern for a cubic graph, but we don't know which way it slides. But we can put this information together with other factors to be able to graph things. So we got a couple of homework examples. We know this is a degree 1, 2, 3. And you notice if I were to expand this, the leading coefficient would be just the exponent, or the number part on the x cubed, which would be a equals 1. So it's, I can tell cubic, it's degree 3, it starts low and ends high, right? So I know it starts low and ends high. And these are known things from the other day. But I also have now, I know what the x-intercepts are. in factored form, I can see them really quickly. -3, 2, and 5. They're always opposite. You think of what makes each of these brackets 0, and it's the opposite value that does. And so what does that mean? It means at those spots I can put points. So I know it starts low and ends high and goes through these points. And say, well, and from what I just did, all of these are slash roots or single factors. So that means it's either going to slash through this way or slash through this way. It's going to slash through this way or slash through this way. Well, how do we know which? Well, think about it. If it's got to start low and slash, it's going to go through like this, isn't it? And then I can sort of connect the dots. It's going to slash through here and slash through there. It's got to do that. So, well, how did I know how far to go up? Well, I didn't really. I just sort of drew it natural, and I'm going to worry about the scale on my y-axis here in a second. And how I do that is I'm going to find another point. And then I can finish off my sketch. Well, what do I mean? Well, usually I like picking the y-intercept. That would be a nice point to know what that is. When x is 0, y is, I'm just substituting in here, and that is the value 3 times -2 times -5 is positive 30. So even though the scale was pretty messed up, that's the point 30. And notice that this gives me a lot of detail to my graph. Great. Well, what don't I know? I don't know how far I went up there. If I wanted to, I could pick some points, like what's the value of the function at 3.5, and I still wouldn't be sure that I got the minimum or maximum, the turning point there. I don't know. So when am I going to be able to know how far to go on my graph? That's not till calculus. So sorry about that, folks. We won't know how far to go up or down until calculus. But, geez, that's a lot better sketch than what we were able to do the other day. Well, let's keep going. We got a couple more examples. Pretty much all of them are the same, though. Now, what's the degree? And I'll do the analysis from the other day. There's 1 there. This is a double root, so this is degree 2 and 3, and then degree 4 altogether. I can see that my x exponent would be 4. 1, 2, 3, 4 altogether. So degree 4, and I know the leading coefficient is going to be 1, or -1 actually, because of this minus in front. So that means I know it starts low and ends low. Starts low and ends low. Starts low and ends low. And what else do I know? Well, I know some x-intercepts, right? My x-intercept is, this one is -5. This one is -2, and it's a double, right? So this is a bounce at -2. But notice that this one gets some people sometimes. This also contributes a 0. This is x equals 0. What makes this bracket 0? Well, x equals 0. And so that means I can put these points on there. So I've got -5 is a 0. -2 is going to be my bounce root, however that works. And 0 right there, -2. And again, I don't put any scale on the x-axis there, or the y-axis rather, because I'm just going to go natural. This is like I'm going to draw it naturally and then put in a scale later. Well, how do I know? This is a slash root at -5, but it can't go this way because it's got to start low. So I know it's going to come through this way, and I know it's a bounce root at -2. So it could bounce this way, or it could bounce this way. Well, it's got to bounce this way to meet up with the graph over here. And this is a slash root that ends low. So even though this is kind of going to look a little bit funky here, I can fill in the blanks. Say, okay, dandy, I don't know how high these bumps are. Well, remember, that's not till calculus, but certainly we could find a point to get some scale. So let's put a point on here. notice my usual choice is I like putting x equals 0 in there, my favorite choice, but I've already got that point on there, so I need to put a different point on there. It doesn't really matter. Any point will do. Maybe x equals 1 because that's the next lowest choice, but then I end up with a big number. And notice this calculating a point is a nice check to see if you got your slashes and bounces right, because notice that we don't know what the scale is, but it should be a negative number, and it is here. Negative 1 times 3 squared times 6 is negative 9 times 6 is negative 54. So look at right there, that point is the point 1, negative 54. So that little distance there is negative 54. So these hills, even though they don't look like much, are pretty big. We got one more, and no graph to do it on. So I guess I'll just try and put it. I'll maybe goof up the scale a little bit here, but I see it. This is another degree 4. Degree 4. It starts high and ends high. I know that because there's no negatives in here. They're all positive brackets, and my leading coefficient is going to be a equals 1. I got x-intercepts at x equals 1 and x equals minus 4, and this is a triple root. A triple root or a slide. So over here I got my 0 at, and that's a slash root there, and a slide root at minus 4. Slide root at minus 4, and I know it starts high and ends high. Starts high and ends high. So what is that going to look like? At minus 4, I know it's got to start high, but slide. So I'm going to exaggerate this a little bit. See how that kind of looks like the cubic near x equals minus 4? Dandy. And then I know this is going to go through here at a slash root because it was only one factor there, slash root. And because I put scale on for my green graph, this is going to be a little goofed up, but that point right there would be my point to get some scale. My x-intercept, or sorry, my y-intercept when x is 0, y would be 0 minus 1, 0 plus 4 cubed is negative a whole bunch, negative 64. And the scale's not quite right, but I'm going to put it on there anyway just because I forgot to put another graph in there. So there's that equation right there. And the homework today is actually on the flip of the investigation sheet and an FAQ, and then bada bing, bada boom, done. Awesome.